Hello everyone and welcome to EMOX webinar series. My name is Ahmed Kabir. Today's topic is how to simulate a spherical motor or a multi-degrees of freedom electric motor. Okay. Alright, so today's agenda, we're going to talk about what is a spherical motor, what are the application and the function of a spherical motor and why spherical motors are needed. And then we will dwell on design challenges, why it is challenging to actually design and manufacture spherical motors. I will go to a 2D degrees of freedom spherical motor with full details. We'll give you some results and then we'll show you some of the EMOX EMS simulation results. Then we go straight to a live demo of the software and Q&A, where you'll have a chance to ask all of your questions. Okay, let's start. Okay, so what is a spherical motor? A spherical motor is a motor that can move along many degrees of freedom. Okay, so unlike a non-spherical motor, okay, that regular motor that we know, basically it rotates along X, Y, or Z, or goes along X, Y, or Z, or any other axis, but just one axis, one motion at a time. It's a 1D, what we call 1D motors. That's 99.99% of motors you see today are 1D. But so how would people do if they need a complicated motion? Okay, so traditionally people use many 1D motors. So if you want to achieve a motion around the XY axis, you will have a motor that rotates along X, another motor rotates along Y. Okay. And of course, there are some mechanical options using spherical bearings and all of that, and we know their disadvantages. So the electrical spherical motors is a lot more advantageous than the mechanical counterpart. Okay. So how to achieve it is by properly exciting the coils, by designing the proper coils and exciting them in a certain series or sequential or simultaneous way. You can actually achieve a spherical motion. And there, as you can see here, spherical motors are really needed, especially for robots, where you have a very sophisticated motion. You can move along one axis at a time, 2, 3, and you go along X, Y, Z. You can actually move along all 6 degrees of freedom if you want to really design sophisticated robots. Some of them are shown here. It can be either controlled by AC current or DC current, and the application are many: medical and surgical manipulators, robots in oil and gas, instrumentation, industrial machining and printing, and automotive powertrains. So there are so many applications, emerging new applications that actually need spherical motion, need multi-degrees of freedom electric motors. They mean exactly the same thing. Okay, so yes, they're interesting, but they're very challenging to design. How to achieve and control degrees of freedom. Okay, that's the main challenge. Actuation method, is it magnetic bearing, core excitation, how to control speed, position, torque. All of those are design issues, are difficult when it comes to a non-traditional motor or multi-degrees of freedom electric motor or spherical motor. They all mean the same thing. You have to worry about the complexity, structure, weight, cost, and the nonlinearity of inter-axis coupling, because sometimes you move around one axis and you affect the torque around another axis, so that's also a very delicate issue. The initial conditions and materials. So these are some of the challenges, and let's see how EMS can actually answer or resolve many of these issues. Okay, let's take an example. So this is an example of a 2D spherical motor. Okay, so you have the rotor made up of cylinder with 4 pole magnets, which are magnetized radially. Okay, and as you can see, we want to achieve a motion around X and Y. Okay, the stator is complicated. Rotor is very straightforward. Stator, which is really complicated, have 18 windings, broken down to 3 separate blocks. Each block, as you can see here, these are the blocks. Okay, each block, as we can see, let's go back to here. Each block has 6 coils, and you're going to see it later on in the actual real model. And each coil has 90 turns and 1 amps current when they're excited. Okay, so to understand the nature of the motion, we ran a no load analysis, which means that there is no current in the coils. And you may ask, so how all moves? Well, we kind of fake it. We say, okay, let's assume a motion anyway using parametric analysis or the SolidWorks Motion. Okay, and we actually move the rotor. Okay, without exciting the current. Just wanted to learn how the motion affects the torque as well as the fluxes and all of that. So one first set of results we're able to do, and again, this is a no load analysis. We'll show you the load analysis, just bear with us. So, and the air gap, we can, of course, the air gap is very important. We can, for instance, plot the magnetic flux density along this red line, as you can see. Okay, we can take any other, let's say, mid gap, this along this circle. You can see, because you know the air gap fluxes are very important for electric machine in general. So we just want to show you how to what type of a plot you can obtain using EMS. Okay, now it comes the exciting part, and the whole idea and the whole cleverness, okay, all people who designed this, we didn't design this, we are just simulating it, okay, is to excite. Okay, so in this case, the yellow coils are excited. By exciting the yellow coils and leaving the other coils with zero current, okay, you can actually achieve a motion around x-axis. Similarly, if you excite this other set of coils, you can achieve a motion around y-axis. So the whole idea is how to excite the coils and which coils to design. That is the cleverness of this particular design. Okay. So first of all, we did the 1D motion around the x-axis. So we just excited the coils in yellow shown on the left side earlier in the previous slide. Okay, let's go back to it. By exciting these coils, okay, we are able to achieve this motion around the x-axis. Okay, and the torque around the x-axis, as you can see. And this other software can do. Let's just be clear on this, okay? Because it's a 1D motion so far, okay? And this one is 1D motion, again, around the y-axis and the torque, okay? And this one is the torque x and the torque y. Okay, now if you want to do a motion setup where you achieve a motion along 2 degrees of freedom around 2 axes, and this is a setup in SolidWorks EMS and SolidWorks Motion, okay? Now in this, just showing you the x-axis displacement and the torque around the x-axis. This is around y, and now these are basically flux density around x and around y, and this is the animation of the flux around x and around y, and these again, okay, sequential motion. You achieve, you excite the x, and after a certain time you excite the y coils, okay? All right, now this one is simultaneous excitation, where we excite the x coils and the y coils, and this is what you achieve. So you achieve a motion around x. It rotates 19 degrees, and the y-axis, it rotates 10 degrees, okay? And this is the actual motion, okay? So this is the ultimate result that you want to show you today. Is now by exciting x coils and the y coils, you are able to achieve this sophisticated 2D motion, as you can see, and the torque as well, okay? So this is torque, and this is, of course, it's a transient solution, okay? All right, now let's move to the actual software, okay? All right, so EMS is integrated inside SolidWorks, okay? So you don't need to worry about geometry. No need to import, to export, to heal the geometry, to fix it, to clean it. Everything is integrated. So this is your SolidWorks, and this is EMS. That's what we call add-in. On top of that, we make use of the SolidWorks Motion, and you cannot achieve multi-degrees of freedom motion without using SolidWorks Motion, okay? So let's just show you how we do the coupling of SolidWorks of EMS to SolidWorks Motion, okay? So creation of geometry, we're not going to cover that. It's straightforward in SolidWorks. It's the number one 3D CAD system, but just show you how we do the coupling. So this is your what we call a study, okay? And this we call X motion, and then this is the coupling, okay? In the coupling, okay, you choose which is the moving part, which is definitely the rotor, and the band is just the air gap around the moving part. You choose to which motion study you would like to excite. So in this one, we say we want to excite, we want to couple this study to motion around X in the SolidWorks Motion. And that's all it takes to couple EMS to SolidWorks Motion. So this is my SolidWorks Motion. If I want to display the motion, so there you go. Okay, so it's a rotation around axis, okay? And the other motion separately is rotation around Y, Okay. And then you have the combined motion along, you see, two what we call motors in SolidWorks Motion, and there you go. It's a 2D rotation around X and Y at the same time. Okay, so so it starts by creating proper motion in SolidWorks Motion. Then you go to EMS and say to which motion study you would like to couple your study. Okay, now the material, so the separator ring, I can show them. Okay, this including the separator rings. If you want to hide the separator ring, these are separator rings that are in stainless steel, but the stators, okay, are actually steel 1010. So applying material is really straightforward, right? I mean, it's just we have many videos in our YouTube channels. What they show you, actually we have hundreds of videos, and many of them they show you how to do step by step, how to apply material, how to apply excitation, so on and so forth. So we're going to skip that part today. All right, so we have now these 16 coils. Okay, so to achieve the X motion, so we're going to excite these coils. So I'm going to do I'm going to show symbols, okay, or you can hide symbols if you wish. So these are the coils that we would like to excite. Okay, by exciting these 4 coils, okay, we achieve a motion around the X-axis. The other coils are suppressed. They're there, but they're suppressed. Okay, which means they have zero current. Okay, and again, just show you how to to specify a coil. You just specify the body and the phase, the entry phase, and the general property and the current excitation. Okay, this is the how, and then we say, okay, you're going to apply these coils. Okay, so the first set of results are table results or tabular results. Okay, so let's see. So this one is a motion around X-axis only. So show you this results, the motion results, they come straight from SolidWorks Motion. Okay, and for each position, okay, these are our SolidWorks Motion, this angular displacement, angular velocity, angular acceleration. Okay, either you can see them in our table or you can refer them. They're the same results from SolidWorks Motion. We are actually getting those results from SolidWorks Motion. Okay, now let's so for each position, each time step, we have all of these results. We have the force, the torque, the current, inductance, flux linkages. So inductance in this case is a 4x4, flux linkages, induced voltages, losses, and so on and so forth. And any one of them you can plot as a function. Let's look at the torque. The torque in this case, you want to look at the torque around X-axis. Okay, so this is our torque. Okay, along the X-axis as a function of time, or if you may, I can also plot it as a function of the angular displacement. It's the same. Okay, and this, if you want to look at the actual results data, you can look at the table results. So at each time step or each angular position, of course you can save it, you can export it, you can all of this stuff, you can save the plot and export the data and so on and so forth. Okay, so any of these quantities are plottable as a function of time or position. And the whole results table can readily be exported for all time steps or for particular time steps. Of course, you can print it. All right, let's look at the field data. So first field data is the wait, let's see, look at wait. Okay, so you have many choices of plotting the field, the flux density, or any other quantity, the H, the applied current, the current density, so on and so forth. Okay, so we have the fringe plot. You can do a clipping and no clipping. Okay, you can do vector plot, streamline, 2D plot. Okay, so any one of them are available for all plot types. So this is the magnetic flux density. Okay, and if I want to see only in the rotor, I can definitely do that, and I can actually animate. All right, so there are about 101 time steps or angular position. Let's see this motion, okay, around, and there you go. It's slowly moving, but surely. Okay, I hope you can see it. It's moving along the x-axis. If I want to do a 2D plot, I can simply, if I want to see the actual field values there along this 3 points, there's 3 segments, okay, and they can specify the time step, and there you go. Okay, so this is my magnetic flux density along a segment, okay, as I showed you in the PowerPoint. So anywhere in the model I can choose any segment. I can also there is also what we call probe. Okay, so if you want to see the values, okay, you can probe the values. Okay, so there's so many options. I don't think I have time to go over all of them, but I encourage you to go to our YouTube channel and to see the full features of the post processor. If I want to do, say, a fringe section clipping, okay, so if I want to, okay, there you go. If I want a section, okay, if I want a section only, okay, I can move my section up and down, okay, and I can actually animate, but this time around versus sections. So EMS takes, as you can see, many sections and shows you, animates how the flux density varies along the different sections. That allows you to see if you are reaching saturation, the values at different position. Okay, I can also do a vector plot, no clipping. There you go. This is my vector plot. Okay, at each time step. Okay, I can do the same thing for H. Okay, and for the applied current, okay, force density, so on and so forth. So all of these plots are available for all of them. See, this is what we call field data. Okay, now let's look at the y-axis motion now. The y-axis motion, it's exactly like the x-axis motion, except material are the same, except now coils 1 to 4 are suppressed. Okay, and I'm exciting these other coils. Okay, all right, so I'm exciting the Y coils. And again, I can look at my results. Now I want the torque around the y-axis, and this is my torque around the y-axis. It's a function of time. Okay, and all other plot that I showed you earlier are available also here. There's no difference actually. Everything is available for this study. So I'm doing a motion now around Y. Okay, so it is moving, okay, around the Y-axis. There you go. And so far you may say, okay, we can do this in other software packages. Yes, you can. Okay, but this is the interesting part. This where you excite the X coils and the Y coils. And in the force, here, by the way, this one I'll show you, okay? You say you want to couple 2 or 3 dimensional, so you want to couple to both torques around X and around Y, okay? And the way you couple to the SolidWorks Motion is just the same, except now you will say, okay, I want to have a coupling to the XY motion study, okay? And there you go. So, and then let's see now. So definitely you're going to have a motion around X, torque around X, okay, and a torque around Y. So there you go. This is what I showed you in the PowerPoint. So you are achieving almost close to each other torque along X and Y, okay. What else? Now I can show you now this plot, and you can see there you go. It's a 2D motion. It's around X and Y at the same time, and this I show you there's no other software can do this, okay? And thanks to SolidWorks Motion that allows us to do this, okay? By the way, you can do more sophisticated. I just wanted to show you rather a simple example, 2D motion, okay? So as you can see, I can actually because I'm coupling to this motion study, which I'm gonna animate again, okay, I can, okay, do this motion along X and Y, okay. I can animate again here. I'm going to show you another interesting plot. Is if I do a fringe plot, section clipping, okay, and that's going to be really interesting to see, okay. A plot on section only. If I want to choose a different time step, okay, and now I'm going to animate versus cut. Okay, so that's what we want to show you is this powerful piece of software that allows you to do spherical motion. And again, I'm just showing you 2D motion, okay. You definitely can do more because you are in SolidWorks Motion, and SolidWorks Motion allows you to do a very sophisticated motion. You can also add springs, you can add dampers if you want. This is force. You can add gravity, you can contacts, gravity, so on and so forth. So with this one, you can, as I showed you, and to the way you control the motion, okay, is by exciting the sequence of coils. And in this case, you have to excite both X and Y coils to achieve the rotation around X and Y at the same time. Last but not least, you can generate a report. Okay, you can put a company logo, your name, company, and you can generate a report. The report is going to document for you your work. Okay, so the pre and post processing results are all dumped into a file, nicely formatted file that you can definitely share with other people. Okay, there's another feature that I want to show you is you can run all studies. So if you want to do many different studies, okay, and before you go home in the evening, you can run all studies. You can duplicate a study by drag and drop. Now I'm just copying everything of that study. Okay, it takes a minute because it has a lot of data. Okay, so okay, there you go. So now this is my copy of this study. I can for instance, if I want to unsuppress this, first of all I have to unlock the study, okay, and then I can let me see, I have to unlock the study. Unlock, to be able to change it, you have to unlock it. Okay, and I can do any change I want in this new study, which so I don't need to reapply the material, coils, and so I can create as many studies as I want, and then I can run all studies. So in this particular case, if I want to unsuppress this code, say unsuppress, okay, results will be invalidated, yes. Okay, so now I have a unsuppress this coil, okay, and I can do different studies if I wish. Okay, so if you want to have an example or problem that you have a spherical motion that you want to try our software, or you want to give it your problem, and we'll be glad to actually simulate it for you. It can be even a 6 degrees of freedom. We are confident using the SolidWorks Motion and EMS together, we can really do a very sophisticated motions. Okay, and for most applications, definitely, you know, we are not there yet. I mean, 6 degrees of freedom are really very advanced, but I think now 2 and 3 degrees of freedom you're gonna soon see, and if not already, some industrial application where you're gonna have some innovative electric motor, then you can do this type of motion for you. With that, I would like to thank you all for your time, for bearing with us, and now it's the time to ask your questions. Just type your question on the right hand side of the chat region, and we'll be able to answer all of your questions. Thank you again.